Hi everyone, my name is Ben Rogers. I used to be a physics teacher for 18 years. I taught at high school, year 7 to year 13. But over the last 9 years, I've been predominantly primary based. So what I wanted to do was to summarize what I think are the big takeaways that I hope would be most useful for you as secondary teachers, secondary physics teachers, um, about what you can expect your year 6s, your year 7s coming up to be able to do and to know. But also I wanted to explain why I think when you ask them directly, they will look like they have no idea what you're talking about. Anything they've done in primary school. It's something called file transfer, and I want to talk about that. So the first thing I wanted to do was to ask you to reflect on whether your children coming up to year 7 act as if they are blank slates. And I've seen it. I've seen kids come up that I've known, that I've taught from year 5 and year 6, come up into year 7. I've observed a year 7 lesson where the children are looking at the teacher absolutely blankly, claiming, hand on heart, they have never heard of something that I know they could do really well. I've got evidence they could do really well just 6 months earlier. So something's going on there, and I'm going to argue that it's something called file transfer. So if I quickly explain what I mean by file transfer and near transfer, when you are taking an idea from one context to another and applying it in a slightly different context. So, for example, I've got here, if you're talking about planets and gravity and spheres and so on, and then you say, okay, well, let's take what we know about planets and study about moons instead. I would say it's relatively close transfer, near transfer. The idea of a planet will help you understand the idea of a moon quite well. If you go the next level up, which I've got here, if you were to explore the ideas of energy and electricity and then say, okay, now let's have a look at the idea of energy in forces of motion, that's a further transfer. Your students might have a really good understanding of energy when you're talking about electricity. As soon as they try and apply the same knowledge to another topic, it's as if they've never heard of it before. You'll have seen that, I'm sure. Then you go up to the next level, and energy is another good example, but it could be particles. What you've talked about in physics, and with slightly different language and slightly different context, say chemistry, they'll look at you as if they have no idea what you're talking about. If you were to do something even more extreme, like talk about physics in a history lesson, or the other way around, then even if they've studied, let's say they've been studying about late Victorian period or World War II, and you're talking about something in physics from around that same sort of period, or we're talking about particles, maybe radioactivity, then they will not be able to match those together. Or they might, but it's hard. That's pretty far transfer. And by the time you're trying to talk about physics and art together, good luck to you. So that's far transfer, and it doesn't mean they don't know it. So if your art teacher starts asking about, oh, what are you doing in physics? This is just like that. Or this is, your cubism was happening at the same sort of time as quantum mechanics was being. They'll look at you like you've got no idea what's going on. Now that's all very well, but that's not what we're talking about with changing from primary to secondary. But this paper that I've got down at the bottom from Barnett and Cece from 2002 looks at other ways that knowledge is hard to transfer from one situation to another. So, for example, you'll have seen this, if you teach something in a lab and then the next lesson you happen to be in an ordinary classroom, that will be harder to retrieve than if they were sat at the same seat. If you're in a different school, imagine how hard that is. You were sitting in your rows in your primary school, and then 3 months later, you're sat in a different classroom, potentially even in a science lab, and being asked the same question. That physical separation from where you were in your primary classroom that you're really familiar with to a new science lab, just being able to recall that answer, that same question that the fingertips knowledge, it will be much harder to retrieve. And that, the Barnett and Ceci was saying, if you took it to a museum, or you asked the same question outdoors under a tree, if you were doing, I don't know what you might be doing, parachutes or something, then they will not be able to make that link easily at all, even though they're really familiar with the knowledge. They'll look at you blankly. Social context. So if the child learnt it individually, they're practicing it individually, they read it from a book or something, and then they will be able to apply it more easily if they're still working on their own than in a pair situation or a small group. Now, if that's a familiar class or familiar pupils, that's easier. But again, if it's unfamiliar pupils in a new class, being able to retrieve that knowledge that they had at their fingertips not long before, that will be really hard to retrieve. So again, it's not that they don't know it, and I'm going to make the case in a moment that if you assume they don't know it and start again, you're wasting a heck of a lot of time. Whereas if you do something about bridging, so if you go and check what they should have known, or if you're familiar with what they should have known 3 months ago, and they look at you blankly, what you need to do is work from where they work your way back. So go back to get them to pitch either. I mean, the ideal would be to show them an example of the work they did, to have their exercise books, or you were in the classroom when you were observing at the end of their year 6, if you had exam release or something like that. You talked to their teacher and you knew what they did, and you looked at their curriculum. You could say, okay, I know this is, you would have looked at this slide when you learnt it in your primary school. They will then be able to make that bridge from that classroom into your classroom. I have another one. So blank slates, no. Transition makes it so much harder for pupils to remember things they had at their fingertips, and apply it into or even to recall it, to retrieve it. And I've got here my little list of things that might be different. There's bound to be more. I don't underestimate rules and routines, terminology. I think quite a lot of them think, oh, my primary school teacher wasn't a science specialist, and so maybe it was wrong, or maybe they just can't retrieve it at all because you're not the same person. Okay, so bear that in mind. I think that's my first big takeaway from this, that when your kids come up from primary school, they probably know an awful lot more. And if you go back and reteach it, A, you're wasting a hell of a lot of time, but B, at some point they'll go, oh, I've already done this, even though you might have had 2 lessons to get to that point. But then you might not realize, and you just carry on as if you've got another 4 weeks of this unit, you're just going to carry on. So don't just do a pop quiz at the beginning and go, oh, they got 0, I'm going to start from scratch. They will not necessarily know what they know, or be able to retrieve it because of those contexts. Big thing to learn. So what is it that you can be sure that they know? And I'm going to argue that you can't be 100% sure they know the national curriculum for science, even though actually I think that's going to be getting better and better, because the Ofsted current Ofsted framework is all about the curriculum and making sure that children know what they've been taught, what the national curriculum says, or the curriculum says, and they know it. So I think currently science is a little bit wobbly, but moving forward it's going to be tighter and tighter. But actually you can be 100% sure they know about anything that was in the SATs. And again, they might look at you blankly because this is a different room, but I guarantee that's any primary school in the country will have spent a significant amount of time on the following things. So let's start with maths. And what I thought I'd do is go through this was a 2019 maths paper. They do 2 1-hour problem-solving maths papers, and so this is a selection of questions that might have something to do with science. So here we go. Really straightforward question. What does that say? Well, actually, it's perhaps not that straightforward. You look at it, they have to infer where that 2 was and how much further that is. That's it's 2.5, but you have to do a little bit of thinking to get that. This would be considered an easy question. It's quite near the beginning of the paper. And the majority, I think we're talking about 70-80% of kids would be able to do this. Have a look at this one. It makes your head hurt, I think. Please, but again, question number 9, you can be pretty sure that kids would be able to do this, majority of children. What you probably want to do if you're interested is go to the primary, find your year 6 teachers, if you can, and actually ask them what their method is for this. I think it will be some sort of write it out forwards and then do it backwards kind of visualization, but different schools might have different solutions for this. Rounding, significant figures really. Percentages. I mean, I would imagine that you would ask. I mean, chemistry. I'm thinking more about percentage yields and so on. But actually, they were able to do this. The majority of children, let's say 70% of kids. I'm pulling that figure out of the hat, but I've got reason. 70% of kids would be able to do this at the end of year 6, even if it was a little bit of a cramming thing. But actually, normally the whole of year 6 has had a lot of focus on this, and actually year 5 as well. Just if you think about how seriously you take question preparation from year 9, 10, and 11 for the GCSEs, and work that back. That's what's happening at primary. You will, in maths lessons, they will be practicing this sort of thing, and they will be able to do it. Unfortunately, it will almost never be in a science context. It will always be favourite jelly. It might be something you want to talk to your primary school teachers about, but putting in more sciencey versions of the same thing, so the kids get more experience at science context, and you've got less of that transfer by the time it comes up to year 7. This question is a really interesting one. I think has real implications for how we teach science and some problem solving in physics. So the question's about a juice machine that pours 250 milliliters of juice every 4 seconds. And the question is, how many liters of juice does the machine pour every minute? So there's a couple of things going on. You've got to transfer how many 4 seconds in a minute, and you've got to change milliliters to liters. So the technique that I expect a primary colleague would use for teaching this, and bear in mind again, more than half of the children that have come up to you in year 6 are likely to have got a question like this correct. Now, there's a visual way of using it that primary school teachers often use called the bar model. If you're not familiar with it, I think it's hugely powerful. If the children you've got don't already know it, then I would still strongly recommend you using it. If they do know it, you've got a real head start. So what I suggest here is that you draw the first volume as a block, so 250 mil as a block, and then what's going to happen is that's 4 seconds, 8 seconds, 12 seconds. To get to 10 of those blocks will be 40 seconds, and then you'll still need another 20 to go, so that's another 5. So what you've got here is 15 blocks making up 60 seconds, and that's a really visual way of showing it. So that's part 1 of it, and what it's asking is how many liters does the machine pour every minute? Well, that's a liter, 4 of them, and so 4 of them is 1 liter, another 4, and you can see you've got 3 out of the 4 there. So it's 1, 2, 3 and 3/4 liters. And what it's doing is allowing you to repeatedly add in a very visual way. And so you've got your purpley bar, your pinky bar, representing that 1 minute's worth of liquid. But you could use this in anything where we're talking about rates, aren't we? Anything where we've got rates. So that could be you're traveling at, I don't know, 10 meters per second. How far will you have gone in a minute? So you'd need 10 meters, 10 meters, 10 meters. You'd need 60 of those. Well, you probably wouldn't draw that, but you could draw a block with and indicate it. You could do an object falls under gravity. The change in speed is 10 meters per second. So how fast will it be falling after 10 seconds? You've got 10, 10, 10, 10, 10, up to 10 of them. So you've got 100 meters per second. So you can see how you might use these. So you, again, rates of reaction for chemistry later on. I would use this for anything to do with rates, and because it's the same maths, this makes it super clear to children, to learner students, that it's actually the same we call it deep structure. The problem solving technique and strategy is the same, and you can use a visual to represent it, and then it's just a case of adding up the bits, and it's really clear and really easy. So it reduces that cognitive load. It reduces that having to hold several steps in your head at the same time. You can do it bit by bit. It's really useful for explaining it to kids, because you're using the same method, the same use of a MAR model over and over again. You may find that your Key Stage 3 maths lessons use it as well, but I've used it definitely up to GCSE, but I can totally see you using it for A level, where anything to do with rates is going on. I think it's really helpful. It's not patronizing, it's just really useful. Another one. So here, a different use of the bar model. This is, we've jumped into the question paper 2. You can see that by the question number 3 at the top. And so this is early doors in that paper. This is actually quite an easy question, but it is algebra, and you may not realize that the children that are coming up to you will be pretty good at this sort of calculation. I don't know, 3/4 of them are likely to be able to get this right. So again, it's another bar model. We got Dev saying he's got £10. That's my £10 bar. He gives some of it away. Which expression shows how much money he's got left? A is the amount in pounds that Dev gave away. So there's A. So he's got £10. He's given away £8. How much is left? It's really straightforward now to see, okay, how long is that bar? Well, it's 10 minus A. So 10 minus A is that one. You can use that for SUVAT. You can use that for a number of different calculations. I would use it for anything where something is conserved. Some money in this one is conserved, isn't it? You've got this £10 at the beginning. There's 10. You've not added money or taken money away. You've given some away. You know how much is left. But it would work with charge. Particularly works well with energy. So you can have your battery as a stores 100 joules of energy. How much of it goes to heat? How much of it goes to electricity? And you can work it out. Okay. Next one, a simple chart. You can see that chart's not your standard form, and they do tend to do it differently every time, which is probably a good thing because it makes you more flexible with it. But just to point it out, and I've not really seen it with these numbers written on before, but just to show you what the majority of pupils will be able to do, what fraction of the 5 days was the maximum temperature below 10 degrees? So there's 2 out of the 5. So that's, it's easy if you know how to do it, and your children do know how to do it, but I can totally imagine them staring at you blankly. Here we've got the mean. What was the mean maximum temperature to 1 decimal place? You can see this is basically the same deep structure as if you've got 3 repeats of an experiment and you want to find the mean of it. Do not assume they can't do it. They pretty much all can, and they've been able to do it since at least year 5, probably year 4. Another one, height of the space station in kilometers. When you're talking about miles, so a little conversion there, they can do that. Now, I just wanted to give you a sense of what percentage of those questions children have to get right to be considered at expected. Now, at expected is a score of 100 in the SATs. So nationally, you've got about 80% of kids, that's girls, that's boys, so it's just under 80% of kids are able to score the expected at the expected level. Now, to get that in those 2 maths papers, you had to get 58 out of 110 in 2019. So more than half of those marks in that assessment just to get the expected score, and 80% of kids can get that. So, like I say, if you've got like 10 form entry, you would expect your top 8 classes at least to be operating at least at this level. I've got here the SATs results from 2019. You can see to get all of them right, to get all of them expected, so reading, writing and maths, 70% of girls got it, 60% of boys. Reading, 78% of girls get the reading. I'm going to show you some reading papers in a moment, but only 70% of boys. Maths is more or less equal. But again, look at that. Grammar, punctuation, and spelling. Bear in mind, the children that are coming to you are really quite sophisticated at their grammar, punctuation, and spelling, and also handwriting. So if you accept lower standards because of this transfer effect or laziness, or I don't know what it might be, but whatever it is, if you accept it, they will do it. So what we normally find, I think, is that from year 6 to year 7, kids' grammar, punctuation, and spelling and handwriting falls off a cliff. So it doesn't take much teaching. If you say this is what you did last year, do it again until you get it good enough, as good as that. It won't take long, and then you've got your whole school career of working at a high level. You don't have to teach them this stuff. You just have to insist that they do it. Writing is done by teacher assessment, and I'll show you how we do it at Paradigm in a minute. There's a rubric, but we also use comparative judgment. Science teacher assessment's interesting and flawed. At the moment, this is what teachers are reporting, and there's very little moderation of that. Sort of 80 to 86% of kids are at expected. But when the government, the Standard Testing Agency, every couple of years do a sample of the year 6s nationally, they find instead of it being 80 to 86%, it's less than 20% are expected. And I think that's subject knowledge. And I think we've got a real problem in this country, but I think that the Ofsted framework, looking at curriculum and looking at the impact of that learning, will be pushing schools into being much more rigorous in their, not only their assessment, but also their teaching of science concepts. So let's have a look. Things you can be sure they know. Reading. Here's a sample piece of text. I'm not expecting you to be able to read that from here. This was a 2016 paper. There's a lot of science, a bit of geography in there. It's a really sophisticated piece of writing. There are 3 of these texts that children have to read in an hour and answer a dozen questions on each one. So it's fast and it's hard. I'll show you an example little section from that. I'll read it to you in case that's not clear. But what is the truth about the dodo? For thousands of years, the island of Mauritius was a paradise. It was spat out of the ocean floor by an underwater volcano 8 million years ago. I've highlighted that in blue. Spat out is metaphorical speaking, isn't it? Who knew that volcanoes could be spat out of the ocean floor? Who knows what an ocean floor is, for example, if you're year 6? By an underwater volcano? Well, who knew that volcanoes could be underwater? But anyway, so there's a lot of, in that one sentence there, there's a lot going on, a lot of subject knowledge that we're expecting kids to have. And they, by and large, they were able to cope with it. With warm sun, plentiful food, and no predators to speak of, the isolated island became a haven for the variety of unusual species, including reptiles and flightless birds. Your kids can do this. They can read this level of text. And I'll just show you how much of it there was. And there were 3 of those. So you can expect them to read, and you can expect them to be able to answer questions on that, and you can expect them to be able to interpret it. If you're not expecting them to interpret it, then and to read text like that in science, they're not going to develop. And in fact, like the handwriting and the spelling, punctuation, and grammar, it will just drop down to the level that you expect. Just wanted to show you something about vocabulary. Tier 2, if you're not familiar, Tier 2 is your sort of newspaper literary language. Paradise, plentiful, isolated. You wouldn't expect to see that in the playground. Kids don't run around saying, oh, look at this isolated haven. It's not done, but they are expected to know it, and you have to teach it. And I think we can't expect the English team to be teaching this all the time either. It's everyone's responsibility. However, Tier 3 is the science department, or geography in this case, department's job to teach. It's the science subject-specific language. Tend to do all right at it, actually. The Tier 2 is harder, and it's one of the reasons we tend to look at a text and go, they'll never get that, when actually they really ought to. Okay, so the next thing that you can be sure they can do is writing, and I'm going to give you an example of the writing that one of our pupils at Paradigm did, year 6 pupil. We'd been studying double circulatory system. I think that's probably too small for you to read, so I'll read it out to you, but this is a single piece of text. Now, this is a 30th percentile. We normally get about 70% at expected. And so this is, we use comparative judgment to score them, to rank them. And so if you had, I don't know how many kids, we've got 300 kids, this would be kid number 90 in that line out of 300. So I'll read it out to you, and I want you to get a sense of what they've done, and I'll tell you how we've gotten there, because this isn't just us teaching the double circulatory system and say, okay, now I want you to write and just let them go. There is some support here, but I want to show you the standard they can achieve when given that support. So if you had 10 forms of entry, this would be a child in your, if you set them all by ability or by attainment, this would be a child in the 3rd set, where 10 is the highest set. Okay, so today I'll be writing about double circulatory system. Before blood is delivered to the blood cells, the blood travels to the lungs. From there, the oxygen gets delivered to the blood, and the lungs receive carbon dioxide, CO2. The organs that are involved is the double circulatory system. In the double circulatory system are the heart, lungs. Can you see there's a colon and semicolon separating that list? So they will know that the heart, the lungs, arteries, veins, and the capillaries. Arteries contain oxygenated blood vessels. Not quite right, but the veins contain deoxygenated blood. The capillaries allow gas exchange to happen. So I won't read more than that, but you can see that's quite a sophisticated piece of writing for a year 6 pupil. But more impressive than that, I think, is that this is not a high attaining pupil. This is a pupil that is scoring around 100, so the expected level, and 70% of pupils plus are achieving that level. So the way we would do it, we would first off study a similar text, not identical, but similar, so that they can get the use of vocabulary, so they can get the sense of some of the sentences you want to do. And here's an example. The diaphragm, comma, a muscle at the base of the lungs, comma, moves up and down. Well, you pick that apart because actually there's something interesting going on in that embedded clause, that would be called. So they could have said, the diaphragm is a muscle at the base of the lungs, full stop. It moves up and down. But this is a better piece of writing. The diaphragm, a muscle at the base of the lungs, moves up and down. You'd look at the sentence, the paragraph structure as well, to work out what goes where. Now, set the task. This is a exploded flow diagram. You've got your introduction paragraph, deoxygenated blood paragraph, and gas exchange paragraph, and you put the little bubbles off, putting what information you'd have in there. So this is pretty, you might do this with the children, or you might get them to plan it themselves with a bit of support. You might do one with them and then do one might do the introduction as an I do, the deoxygenated blood paragraph as a we do. So you might get them to do it in pairs, or you might do it as a whole class. And then gas exchange, they might do on their own. That is the plan that would lead to this piece of writing that we've just talked about. So it's not just setting them off, but at the same time, that's an independently written piece of work. After that, we would then go back. This was scanned and judged. After that, the teacher would then go and do some feedback, and there are a number of ways of doing that. But that some of those misconceptions in there would hopefully be picked up and fixed in the final version, sort of green pen editing type style. Okay, so the next thing I wanted to talk about is that's what I'm pretty sure they can do, and that'll be for all kids certainly in England. What they ought to know, what you would hope they'd know, is the national curriculum for science. Well, like I say, I'm not confident that they do. There's the Standards Testing Authority or agency say that only about 20% of the children that they test know what they ought to know at an accepted level. And that really drops off a cliff by the time you get to kids with pupil premium or EAL or anything like that. So, we're in a bit of a pickle where it comes to what the children actually know. However, I'm confident from conversations with colleagues, and certainly from the work we're doing at Paradigm, that our children coming out knowing much, much more under the new framework as we really doubled down on our curriculum and the subject knowledge. So this is what they ought to know. I'm not going to go through all of this, but I think it's important to see some of the key language. So year 3, talking about reflections with light, talking about magnets attracting or repelling. Quite often primary colleagues tend to use inquiry or investigations to teach some of this stuff. If you know me, you'll know I'm not convinced of that at all as an approach. But I think the problem is you've got non-specialists teaching it, which there are plenty of non-specialists teaching physics at high school. It's not that in itself isn't the problem, but the training that primary teachers get at teacher training is typically like a day. And what can you do in a day? You can't learn all of biology, chemistry, and physics, but you can do how science works or inquiry-based science pedagogy. And so I think that's what happens. I haven't got evidence for that, but other than anecdotal. So year 3, year 4, totally different stuff. There's no spiral curriculum here, thank you very much. Sound, vibration, series circuits, so electricity in year 4, earth and space forces. And now here we go back to light and electricity. So light, you can see I've highlighted a few more things. You've got voltage, circuit symbols, and so on. But just to go back, electricity was year 3. No, it wasn't. Year 4. Light was year 3. And then by the time you get to here, light is year 3, electricity is year 4. They've forgotten all that, surely. Magnetism is even worse. Magnetism is year 3, and we don't repeat it until year 8. Strikes me there's not an awful lot of point learning it if you're not coming back over and over. So I think there's some work to be done here for primary teachers, but and you may want to have that conversation with colleagues in primary. How do you keep that stuff fresh? If they've learned something in year 3 and year 4, how do you keep it going if it's not revisited again until it's year 8? Okay, so like I say, I'm optimistic this will get better, but at the moment I think it's pretty dire. This one is better, but sadly, the language here is not the same as GCSE language. So you'll probably be asking, we've got another example of file transfer. You'll be asking about one way of talking about how science works, and they'll be talking about another, and they'll look at you blankly again. But they have actually probably spent more time on doing fair testing, using simple models, taking measurements and stuff like that, they ought to be able to carry on with you as long as you help them bridge that. Okay, so nearly the end. What's the big picture? I've got 3 big pictures, and I'm going to finish off with a super big picture. So blue one, you can't tell if you're teaching something new or if your pupils are suffering from far transfer. You can't easily tell. I think the best way to go is to talk to primary colleagues and say, what should they know? Look at their curriculum, look at their books, go and watch some lessons if you can, have some conversations. Pinky one, pupils probably have better strategies and skills for maths, reading and writing than you realise. And if you don't realize it, you're likely to underestimate what they can do, and they will descend to that level and you have to build up again. So I think save a lot of time in your classroom, and don't waste all of that really great learning they've done at primary school. Help them bridge. Final one, they might well know more science than you think. They might not, but you won't know until you won't know by asking them, and you won't know by doing a little like a pre-quiz, because they'll answer nonsense even if they do know it, because it's in a different room, it's different, different teacher, different class, might be in a lab, all that stuff going on. They won't be able to remember it. Whereas if you bridged it first and then did the quiz, you'd get a much clearer idea, I think. But the super big picture is, I don't think primary and secondary teachers talk to each other enough. I don't think we spend enough time in each other's schools. But it's not just watching lessons, and it's not just a sit down with some books and have a quick look. I think this stuff takes a lot of time. I think it does. You need, I don't know, secondary teachers. Can you make friends with a primary teacher? Take them out for a coffee. And another thing that I think is slightly toxic about the relationship between primary teachers and secondary teachers, when I talk to secondary teachers about primary teachers, they're very generous, but it's also really patronizing. I quite often hear, oh yeah, we'd love to support our primary teachers. We can do it after the GCSEs are gone. We'd love to support. Well, I think I've shown you today that primary teachers are massively skillful, especially when it comes to reading, writing, and maths. They've got problem-solving techniques. They've taught children to perform really complex problem-solving and writing and reading tasks that secondary teachers, I don't think majority of us know how to do that. And so I really think a really healthy way to move forward would be to learn from each other, just spend more time together and really respect each other and see what we can learn from each other, rather than when we meet, I'll teach you how to do forces. No, it's more two-way than that. All right, hope that was useful. Happy to engage with chats and conversations at Ben Rogers Edu on Twitter, or if you've got my email, benrogers.school@gmail.com, you can contact me that way as well. Nice to see you. Take care. Bye.